Hello, dear participants. I'm glad to welcome you here at our section devoted to micropolar media, complex media, chemomechanics, acoustic materials, and so on. And I should remind all talkers and speakers that we have 20 minutes for presentation, including questions. And the first report is mine. I will talk about boundary layer formation due to the stress-induced diffusion in micropolar media. And my name is Ksenia Frolova, and this presentation will be made together with Vilchevskaya E.A. Okay, so sometimes even small concentrations of hydrogen can lead to premature failure of structural elements and metal details. And local increase on hydrogen concentration also can change significantly material properties and its behavior. Therefore, it is necessary to understand real picture of distribution of hydrogen through the thickness of material. Usually it is believed that hydrogen is distributed uniformly through the thickness of material. However, according to experimental data, it is distributed significantly non-uniform, and according to direct measurements of hydrogen concentration in cylindrical samples saturated artificially with in an electrolyte solution, almost all hydrogen due to hydrogenation is concentrated in a thin boundary layer about 60 micrometers. The same boundary layer is confirmed by an investigation of the fracture surfaces after tensile and fatigue tests of saturated samples. According to this data, according to scanning electron microscope images presented on the slide, we can see that area containing hydrogen is about 3,100 micrometers. Such a phenomenon of skin effect can be described and sometimes described by consideration of material of some samples with different kind of external loading and by accounting for aging strains due to hydrogenation. The other type of modeling considers some kind of subboundary layer containing different traps for hydrogen, like cracks, micro cracks, pores, and so on, and other defects. However, all these models assume existence of such subboundary layer, but they don't describe how can it appear and doesn't model it. So they just say that it exists. Here we try to explain and to model appearance of such boundary layer with the stress strain state that differ significantly from the bulk material. So we start from the mass balance equation for hydrogen and consider stress-induced diffusion. We assume the diffusion flux consists of two terms. The first one is due to gradient of concentration, and the second one is due to additional driving force. Here, as usual in hydrogenation problem, we consider pressure as additional driving force. And additionally, we assume dependence of the diffusion coefficient on the elastic strain energy to account for the influence on the stress strain state on the diffusion process. Here we want to obtain subboundary layer with stress strain state that differs significantly from the bulk material. And here we use micropolar theory of elasticity since it has been already applied a lot of times for a number of problems with size effects. Particle in micropolar media can be considered as an infinitesimal solid body with independent rotational and translational degrees of freedom. Therefore, stretch tensor and dryness tensor are introduced, and constitutive equations are written for stress tensor and coupled stress tensors. Here we assume that hydrogen can lead to aging strains and use Domain-Neyman constitutive equations for stress tensor. And we solve two balance equations. In particular, we consider specific case of micropolar media, namely micropolar media with constant rotation, where independent rotations are absent and non-classical elastic modulus kappa goes to infinity. In this case, it is necessary to find antisymmetric part of the stress tensor directly from the balance equation, not from constitutive equations. We solve boundary value for a long cylindrical sample to model real experimental data that we have. And here we take into account axial symmetry, assume that all cross sections behave the same, and also use principle of linear superposition while talking about axial displacement. So we consider axial displacement as a sum of two terms. First term due to micropolar solution, and second term is due to non-homogeneous distribution of hydrogen. And we use the following boundary conditions. We assume that the lateral surface of the cylinder is traction-free and also set couple, distributed couple stress, or micro-rotations that model rotations of real rotations of regions between microcracks. We also assume that axis is fixed and find radial displacement as usual, and use Saint-Venant principle and use integral boundary condition at the end faces of the cylinder. And as for boundary and initial condition for concentration, they are the same as in experiment. So we solve the following system of equations. The whole system was solved numerically, and additionally we solve analytically the first three equations that describe stress strain state of a non-saturated material. While talking about analytical solution, we took into account that solution has boundary type solution, is boundary type solution, and therefore only blue terms are present in equations because of asymptotic assumptions. And the same was done with micropolar media with constant rotations, also only blue terms are present in equations. And here, instead of non-classical material constants, we use engineering constants, namely coupling number, characteristic length for torsion and for bending, and polar ratio. When coupling number is equal to 1, we deal with material with constant micropolar media with constant rotation. And values of characteristic lengths define the thickness of the area where the couple stress is active. So here you can see the analytical solution with two types of boundary conditions, kinematic and static boundary conditions. Solutions drop exponentially to 0 when we move out from the lateral surface. And the region of this drop depends on the non-classical material constant, or engineering constant in our case. And hereafter, we deal only with couple stress on the lateral surface and restrict ourselves to consideration of bending on the lateral surface. So we deal with the solution for axial displacement and micro rotations around port E5. To estimate non-classical material parameters that are not known from experiments, we assume that solution decreases by a factor of k time at the inner boundary of the experimentally known layer in comparison with corresponding values directly on the border. And here we analyze axial displacements. On the left plot, you can see analytical solution for axial displacement. And we can see that the value of the distributed couple stresses affect the value of the axial displacement, but it doesn't affect the thickness of the boundary layer. On the right plot, you can see comparison of numerical results with analytical solution. You can see that they coincide, and therefore one can use asymptotic assumptions to analyze different dependencies in analytical solution. And also here you can see that using of different values of characteristic lengths for bending lead to different thickness of the boundary layer. Here you can see concentration profiles of hydrogen. Black line is corresponding to diffusion with constant diffusion coefficients, and other lines correspond to model accounting for dependence of the diffusion coefficient of the elastic strain energy. And we can see that accounting for couple stresses really allow us to explain the observed spin effect. And here we also can see that additional accounting for edging strains caused by hydrogen red line and for additional driving force by pressure green line don't lead to significant changing of the results. So the main result is due to accounting for couple stress interactions between material particles. According to experimental data, thickness of the boundary layer was 60 micrometers or less. And here we obtain that it is about 20-30 micrometers. Also, I should know that according to experimental data, 60 micrometers contains about 77% of dissolved hydrogen. However, here we obtain that our boundary layer contains all dissolved hydrogen. So further investigations are necessary to describe a deeper diffusion process. At the same time, values sample average concentration and surface average concentrations obtained experimentally coincide with our theoretically estimated data. So our model describes the real experiment not only qualitatively but also quantitatively. And here we investigated influence of non-classical parameters, namely coupling number on the plot and characteristic length for torsion and Polar ratio. Here we can analyze expression for the strain elastic energy. There is no Polar ratio, so it shouldn't play a role. And also we can see that characteristic length for torsion is multiplied by blue terms that are less than red term according to asymptotic assumption. Therefore, it also shouldn't play a role, and we have checked it and obtained that yes, all these constants don't play a role, so only coupling number and characteristic length for bending can affect the solution. Also, we don't have exact values of linear expansion coefficient of hydrogen, and therefore here we checked, we used different values and analyzed the influence of aging strains of hydrogen on the result. So first of all, we can see that the main reason of the skin effect is still non-uniform stress strain stains obtained within the frame of the micropolar theory, not engine strains of hydrogen. However, higher values of linear expansion coefficient can lead to deeper penetration of hydrogen inside the material. And also, according to experimental data, average concentration of hydrogen in materials with less radius is higher, propagated because of the absolute value of the thickness of the boundary layer, I mean value in micrometers, is the same in all cylinders. And our model confirmed this fact, and the ratio of average concentrations of obtained for cylinder with radius of 2 millimeters to radius of 4 millimeters is in the range obtained experimentally. And finally, it is known from literature that sometimes in metal details one can observe plastic deformations in the vicinity of the border. So it was of interest to check if micropolar solution, when we have big values of stresses in the vicinity of the border, can lead to such flow, and in this case it also should be accounted in further models. And here we use generalized yield criterion of 1 millis for micropolar continuum, and usually it is used one criterion for coupled stresses and stresses, or two different criteria for different stresses. And the main question here is about material constants that present in the intensity expression. And here we use different values from different papers. However, it was found that all of them lead to more or less the same result, and we obtained that the area where the yield function becomes negative is about 100 to 200 micrometers. And therefore, yes, it's really necessary to account for possible plastic deformations in the vicinity of the border. And here you can see the conclusions. So our proposed model of stress-induced diffusion in micropolar media allow to describe the experimentally observed skin effect. And here we discussed three skin effects. First is the non-uniform distribution of stresses and strains due to couple interactions between particles. Second skin effect is the non-uniform distribution of hydrogen. And the third skin effect is about probable plastic deformation in the vicinity of the border. So thanks for your attention. Any questions? Yeah, we have some time for questions. Somebody has any questions? You can ask. If not, then
Из чата вопрос можно, да?
Да, теперь мы вас слышим, да. Здравствуйте, можно.
Здравствуйте. То есть вы меня слышите или еще кого-то?
Нет, мы вас слышим.
I have a question. What diffusion mechanism take you into account in your model?
It's just
What diffusion, physical diffusion mechanism?
just a fixed law here. Just fixed law. And here we just consider dependence of the diffusion coefficient on the elastic energy, but the law is usual.
Oh, vacancy or interstitial?
No, we don't use here any vacancies, so nothing specific mechanism.
Interstitial, yes. And what structure material, how you take into account the structure of materials, the presence of intergrain boundary?
Well, here we don't take into account directly grains or grain boundaries because it's a continuum model. So here we account for some specificity of microstructure only by introduction of non-classical material lengths for bending and for torsion in general. So these material lengths, here I use only LB. It is known that its length is about length of the grain. So in fact, by introduction of these material characteristic lengths, we account for the size of grains. And if we obtain that it is about 6 or 13 micrometers, we can say that it is about a half of a grain. But we don't use here micromechanics models and don't account for the structures that contains grains and grain boundaries. So we assume that diffusion is along grains, but here in the model it isn't presented.
And your diffusion layer is equal with the grain size?
Yeah. We have obtained that it is about the grain size, but initially it was just some value in equation. And finally, by comparison of solution on the lateral surface with solution inside the boundary layer, obtained that yes, its length is corresponding to the grain size. Well, okay, in this case, the next speaker, Morozov Alexander.
Yes.
From Institute of Mechanics of Berlin, and his report is developed that is entitled as on stability of propagating chemical reaction fronts in elastic solids.
Yeah, thank you for your kind introduction. It's a bit awkward for me to be at 8 p.m. and in online format sitting in Berlin. So greetings to all of you, and thank you very much for organizers for letting us in for doing our online presentations. So I will share my screen, and now I think it's okay, and you see my first slide, isn't it? Dear organizers.
Да, ваш презентацию видно.
Yeah, super. Then I will start. My today's talk is devoted to the stability and propagation of chemical reaction fronts in elastic solids. This work is done in collaboration with my supervisors, Professor Freidin and Professor Muller, during my doctoral study in Technical University of Berlin. Today, I will talk briefly about the motivation of where this study came from. Then I will highlight how we perform a stability analysis and why it's important for us. And I will show some numerical results which couples our analytical solution with our understanding of what is happening. So first of all these problems appeared from some experimental evidences which show that mechanical stresses may affect chemical reaction fronts. For example, these experiments were observed for self-limiting oxidation of a silicon particle. Similar problems may occur in other industrial applications related to microelectronic devices such as solder walls and solder wall interconnects, where not only mechanical mechanical stresses may affect the gross kinetics of some layer, but also some other stuff like electrical current or thermal gradient. And finally, the problem with which I have started my dissertation was the lithium-ion battery problem, and then we found a paper which stated empirically that silicon particle due to lithiation, depending on the size of particle, may have some cracks, and of course these cracks are no good for our future lithium-ion battery cell. So trying to understand all these phenomena, we were utilizing the concept which was proposed by Professor Freidin almost 10 years ago. We consider a sharp interface, the chemical reaction localized to the sharp interface. We assume that our material star diffuses through the material plus, and the reaction occurs at the interface between materials plus and minus. So far, we assume that all the material star which has diffused to this interface is consumed by the reaction. This chemical reaction is accompanied by the chemical transformation, and so far we utilize the chemical transformation model, which can be by parameter C here, can be utilized as a so-called solid skeleton approach, or another limiting case. So when we fit our experimental data, we choose somewhere in between, because we are not sure what is actually happening there. With this stated, the boundary and interface conditions are for the mechanical problem and for diffusion equation are shown in the slide, and how in our model chemistry and diffusion mechanics are coupled are at the moving interface. So reaction front is happened on the moving interface, and our omega n is what couples everything. Oops. And for this, we utilize, as I mentioned earlier, Professor Freidin's model, which stated that the reaction rate is a function of the so-called normal component of chemical affinity tensor, which for linear elastic solids, in case of small strains, has this form. So basically, this is how we treat our influence of stresses on the chemical reaction rate. Of course, there might be some additional models. For example, stresses can be also taken into account in the diffusion coefficient, but so far we are not using that. So why it is important to take into account the stability? Because this problem is quite similar of the moving interfaces, quite similar to the problem of moving interfaces in phase transition, phase transformation problems. And in this class of problems, the material decides where is our equilibrium and where the initial volume of the transport material will start. So, for example, if you consider a sphere and under some loading, so the nucleation of new phase may start from the inner ring, so the center of this sphere. But in case of if we try to swap this material phases, that would be an unstable configuration. But what we have in our chemical reaction, of course, chemical reaction starts only where the diffusing constituent is supplied. And if we consider a sphere and the diffusing constituent comes only from the outer surface, of course, it's hard to start a nucleation for material inside the sphere. So it will start grow from the outer surface. And in that case, our reaction front can propagate towards unstable equilibrium, and our idea was regarding this fracture of the silicon particle that it may propagate towards unstable equilibrium, and these instabilities may produce this fracture. So in order to deal with that, we started our linear stability analysis, which was first performed for phase transition problems by E.N. Fu. And what is basically done, we consider the position of the interface and we introduce some perturbations to the reaction front. And we linearize our perturbation with respect to the current position of the interface and see whether these perturbations will vanish in time or not. So to do so, we introduce our perturbations and we then plug them into our boundary value problems. Since our perturbations are small, we linearize our equations, and of course we have to update our interface conditions and boundary conditions, and finally, when we will solve our system of equation, we will plug our solution into the linearized kinetic equation for these interface perturbations. Basically, eta here is an amplitude of a perturbation, and this is the evolution law for the amplitude of perturbation. And basically, from this solution, we will find out, okay, if this amplitude of perturbation will vanish in time, then our solution is stable. If it will grow, then we consider it as an unstable. So how to treat all this model? We consider cylindrical chemical reaction front. So we consider reaction in a cylinder. We apply some load of the external boundary condition, external surface of this cylinder. We consider that our chemical transformation is plane, and that was done only for the convenience of the analytical derivations. So it's not a problem to introduce the full in all directions this chemical transformation involving. So this elasticity boundary value problem is pretty straightforward. For the diffusion, we consider diffusion only in the material class, and boundary value problem for the diffusion is also shown on the slide, and the reaction rate is what is coupled, is the model which was on one of the first slides. And finally, what we are actually solving, our kinetic equation, we treat our velocity, and our velocity of the reaction front here will be on the just derivative of interface position with respect to time. So negative sign comes from that we always consider the normal vector is pointing outwards material plus. So then we introduce, so we have our solution for unperturbed interface. Now we are going to introduce some perturbations. And as I mentioned earlier, we introduce them in a manner, so as listed here, we introduce our eta as a function of phi. Then, of course, due to that perturbation, our displacement field will be perturbed, and the diffusion field will be perturbed. And when we plug everything in our linearized boundary value problem, we can solve it, we can try to find the solution in series. And basically, in the end, for each wave number, we will obtain a perturbation solution equation, which is listed below in the bottom of the slide. And from this equation, you see the solution of this is an exponent. And basically, the sign of our Ln defines what it be. So if the sign is negative, then exponent in negative power will vanish in time. So we consider it as a stable solution. If our power of exponent is positive, then we say, okay, this is the unstable solution, physically unstable solution, and wave number, the lowest wave number, n at which Ln is positive would be the failure mode. By the way, I should note that this kind of analysis was performed also for a planar interface problem, and for that case, it was possible to show analytically that the diffusion properties of material does not influence the stability behavior. In other words, only mechanical properties define whether the reactions prone to be stable or not. And having this said, we want to analyze our LNs in terms of like whether they are positive or negative. What is shown in these plots, we adjust our external load to put our equilibrium position at various radiuses. So it means that, for example, on the left slide, we consider a solid cylinder, and a certain load was applied to have our equilibrium position at 0.6, for example. And that means for wave numbers 2, 5, and 20, we see only negative values for Ln, and we consider this configuration is stable. And we see that we cannot prove that all of them will go down, but we see the tendency that very high frequency numbers are even lower. And the opposite we see when we consider unstable configuration, and we see that some effects on the edge appear, but that's limiting case effects, which may be devoted to the problem that if we have a very thin layer of new material and we want it to be stable, it's a bit different problem. So the interface starts to forget that it is a cylinder. So where there's very thin external layer of new material, we may even switch to the planar interface solution. So something is happening here. But with the, for example, for 0.6 and lower plus minus equilibrium radiuses, we see that for an unstable set of material parameters, let's say, all the values are negative, and we expect this configuration to be unstable. Also, these plots are for solid cylinders, and what we started with a whole cylinder problem, and we see that the hole inside the cylinder introduces some instability in the area close to the hole. So if we consider even the hole 0.1 of external radius, we see that if the equilibrium position would be 0.2, it would be unstable, even though material parameters which we are looking at are considered stable. If we introduce a bigger inner diameter, we see that for stable configuration, or even for stable configuration in terms of material parameters, these interfaces will be unstable, just due to the internal hole. And what is mentioned recently, and we're working on the paper right now, that all these results are relevant not only in the equilibrium position, but also at the propagating interface. So basically, we are linearizing our kinetic equation not at the point of chemical equilibrium or thermodynamic equilibrium, but on the moving interface. And to understand what is how the velocities of the amplitude change or growth and velocity of the propagating interface are related, we should consider the following. For example, we consider the solid cylinder, and we consider the configuration at which equilibrium is in the middle of the interface of the cylinder, so low equilibrium is 0.5. We consider perturbations, introduce perturbations amplitude as a function of radius, and as mentioned earlier, our amplitude velocity growth is defined by this equation. And basically, we have calculated our Ln, and we only need an amplitude to define what is the velocity. That is why we introduce some perturbations amplitude here. And to see what is happening in a stable configuration, of course, we want to plot the ratio between these two velocities. By these two, I mean the velocity of the perturbation, so this index should be C, not eta, to the global, let's say, kinetics of the interface. And this is basically the solution for unperturbed interface propagating towards the equilibrium. As we see, we have some extra, at the 0.5 we have infinite, just because our velocity of propagating interface is 0 at the equilibrium radius. But we see that for the stable configuration, at every point of our solution, these LNs are negative. So that means that our interface is stable or unstable. Yeah, thank you.
Alexander, you have 1 minute. So.
Yeah, thank you. For every position of the interface, we see that it's stable not only at equilibrium, but on all the way to the equilibrium, and vice versa for a stable configuration. And the last 2 slides, I want to show you what we have seen in our numerical experiments. If we consider, for example, initially perfectly circular interface propagating towards some equilibrium position, we see that in case of stable configuration, all points of the interface smoothly converge to the equilibrium position. However, if we consider unstable configuration, for a certain amount of time, our circular interface propagates as circular, but at some point these perturbations start to be visible. And this corresponds perfectly to what we have obtained in our analytical solution. So the amplitude, the velocity of amplitude growth starts to be dominant in this ratio here of velocity with respect to global kinetics of the chemical reaction flow. And last slide is if we introduce some initial perturbation to our interface, it remains in unstable configurations. The shape of the initial perturbation remains, however, amplitude grows during the propagation. And that also fits to our analytical prediction. So the unstable interface is unstable at every point, not only at the equilibrium. With this, I would like to conclude that during this work, a numerical procedure was developed and validated with analytical results. Analytical procedure to analyze the stability of the chemical interfaces, propagating chemical interfaces at the equilibrium and on the way to the equilibrium were obtained for diffusion problem, for chemical reaction problem. And of course, this was studied numerically as well as analytically and cross-validated. With this, I would like to thank you, and I'm over with my talk.
Thanks a lot. Dear participants, any questions? Yeah, Alexander Борисович, хочет задать вопрос? Да.
Anna Knyazeva has a question, as I understand.
Professor Muller, you can switch on your microphone if you have a question.
No, thank you. No question.
Okay. So, if no questions, that I think that we don't have a lot of time and we need to continue. And the next speaker is Grigoreva Polina.
Yeah, thank you once again.
Yes, thank you. Okay, Alexander, I'm sorry. One question for you. How do you account for the state diagrams and the sequence of the phase formation? Charge transfer during oxide formation. Why do you study cylindrical fronts? You can also read the question from your chart. I think that you can.
Yeah, I see the question. Thank you very much for your question. First of all, why do we study cylindrical front? This problem comes, well, first of all, it is possible to do analytical model. Second, during the literature observation on experimental data, we have found several studies on lithium silicon nanowire as a node structure for lithium-ion batteries, and there they have shown us the experimental evidence that the reaction was stopped, and that's why we have started with the cylindrical problem. Regarding the phase formation, I'm not talking now about the phase formation. Regarding the phase formation, as far as I understand the question, this is hidden in our chemical reaction and how is defined all these stoichiometry coefficients. And no, we are not taking into account any charges here. So we are working on model for electromigration in microelectronic devices in solar walls, but the electromigration is taken into account in a diffusion term. Yeah, that's true. They have numerous stages, but we reduce it to so far, of course, we can model all of them. And of course, especially for lithium-ion batteries, they have even changed the structure of the silicon particle. For example, as the beginning of the just produced cell, it contains particles of crystalline silicon. After several cycles, we have amorphous silicon, and of course, they have different stages and different mechanics or mechanisms of doing that reaction. So at some point we have to switch to the bowling reaction, of course. And so far we are considering the reaction which has a sharp interface. I hope that I did answer at least some of these questions.
Okay, thank you, Alexander. Okay, if no questions, then we can continue. Thanks again. And the next person is Grigoreva P.M with Polyanski V.A. And the title is Modeling the Skin Effect in Metals Appearing Due to Hydrogen Absorption using various diffusion models. And this. Можете визитовать значок кнопочки какой-то. Правее. Нет. So I'm going to make a presentation, probably in continuation of Ksenia presentation, how to model the skin effect in metals using diffusion models, not some models of behavior of material. So again, just to remind you what are the new challenges in the diffusion problem. The one thing is that the existing models of hydrogen diffusion, they prescribe the diffusion from the aggressive corrosive environment. But recent experiments show that hydrogen diffuses also from the air, from the not high concentrations of the hydrogen. So the hydrogen also distributes non-uniformly and forms a boundary layer. And also we experimentally see high gradients of concentrations, which are not counted in existing models of diffusion, because sometimes the acceptance of the diffusion model is that the concentration, the gradients of concentrations are relatively small. Furthermore, we want to take into account the impact of the stress-strain state of the metal and of the induced stresses and strains. We use the linear non-equilibrium thermodynamics approach, where we write the hydrogen transport equation as a divergence of the flow. And in linear non-equilibrium thermodynamics, this flow is defined as some values multiplied by the gradient of scalar chemical potential. For the system of solid gas, this potential is defined as the sum of the chemical potential, and as the chemical potential of the solid is normally tensor value, we take the trace of this tensor as we consider the diffusion which propagates in all directions. First, why it is good to take this approach? Because in this approach we can take into account all the potentials that can appear in the metal, in the solid. For example, we start with a case of a linear elastic solid, but this chemical potential can take into account the potential of the plastic behavior and so on. So this is a good start to build a related physically described model. So finally, in case of linear elastic solid, we obtain diffusion equation and solve the boundary problem for the cylinder with a prescribed in Excel load and flow on the surface. And also we say that we have induced diffusion strains, induced by the diffusion of the hydrogen inside. But again, we solve the linear elastic problem. So in this case, we obtain some curves that they show that first the diffusion of the hydrogen slows over time. It's quite a good start for building a physical model, not phenomenological one. But the problem is that we cannot describe the high gradients and this boundary layer which we observed experimentally. And the second problem is that with the time distribution of hydrogen flattens. So we cannot say that we have a boundary layer which experimentally is not propagating inside the material. So the idea was to add a source term in the diffusion equation. We want to connect it with the microstructure of the solid, so-called traps in the theory, which can be micro voids or micro fractures and so on. So we want these traps to work as a source term and stop working when they are fully packed with the hydrogen. And we want to add this source term based on some physical process, but not phenomenologically. And of course, we want this source, which depend on traps. We want to depend also. We want it to depend also on stress strain state of the solid, concentration of diffused hydrogen, and so on. Everything that can affect microstructure of the material. So the first idea was to take into account the measurability tensor, which appeared first in works of Polyanski and which showed non-uniform distribution of micro cracks and micro voids in metal. So they introduced this tensor studying metal using acoustic anisotropy methods. And basically this tensor is a tensor form of the measurability, which describes how much of surface of our initial
initial surface, how much percentage of this is occupied with our traps. So what we do, following all the researchers who are studying trap diffusion, we decompose our concentration into the lattice concentration and trap concentration. And thus we can decompose diffusion flow. And saying that we don't have any equations or laws for the flow of, in the traps, it's just additional space for the hydrogen flow. We just obtain the diffusion equation with some addition. The good thing of this approach is that all the components of this measurability tensor can be measured, so we can use experimental numbers. But the problem is that we cannot describe when these microvoids or microstructures will be full with hydrogen and will not work as traps. And also, we cannot predict this dependence on time. Otherwise, we should measure this measurability tensor every second, I would say. So we don't have any laws of how the measurability tensor depends on, for example, time or stress state yet. So probably this is a way to develop this approach, but for now we just took the measured value of the measurability, which was taken as a analytical dependence, and we solved the mentioned boundary problem with a new diffusion equation. So what we see, we here observe a boundary layer which propagates inside the material, but as the value of the measurability doesn't change, the distribution of hydrogen flattens out with the times. So the blue curve is a small time, and green is a big time, and further we go, the latter is the distribution of hydrogen. So we don't obtain here the boundary layer, which is stable. Another common way to consider trapping is again to decompose concentrations in the lattice and trap, and we introduce also density of traps and density of interstitial site. So we can say that if we have somewhere as occupancy, we can multiply it to the density of our traps or sites and have the concentration. So there are two common models which I use widely for the trap occupancy evolution, E.N, which is the first and which is quite bad because you can see that even we have a time-dependent concentration and therefore time-dependent occupancy of traps and interstitial site, we don't have any time dependence into the model for the trap. So therefore, if we have some changes in the interstitial occupancy or trap occupancy, the other occupancy will change in one moment, which is actually not a physical thing. So we use an earlier equation, Foster, which describe dependence of the occupancy of traps, depending on time and occupancy of lattice, where P and K are some material parameters. So finally, we write diffusion equation for our case for linear expresses, and so again we can solve it numerically. So the good thing of this model is that we can take into account the redistribution of traps and see how it changes with the times. But the bad thing is that first the density we should, for this model, we should know the distribution and dependence sometimes of density of traps and interstitial sites. Therefore, we should measure it, but we still don't have any experimental things or ideas or models to measure it. And also we the Foster equation was proposed only for lattice occupation which are quite small, relatively small, pretending that the most of diffusion goes into the traps, which is also quite controversial questions, because if we have a boundary layer with a high concentration of the hydrogen, the interstitial occupancy would be relatively big, and this model would not work. So the conclusions and the direction of the research, that is, well, first of all, that these models, they don't describe probably experimentally observed boundary layer, but we still have some advantages of every of the model, and finally we can just build the solutions to be representative enough of this threatening problems of the transient. I mean, at the very beginning of the diffusion. Another way of research, which was proposed by Freidin, is not to change the diffusion equation, but the boundary conditions. I mean, those for the flux. These ones. So we can introduce some dependence of these constants, or the ability to penetrate, the ability of hydrogen to penetrate, depending on some structural mechanical laws and so on.
Thanks a lot for the presentation, and we have a question from the chat.
Comparison with reactive diffusion models. Sorry, could you please describe what do you mean by the reactive diffusion? Because probably I've seen them, but I just don't know what do you mean by them.
Anna Georgina, please, can you clarify the question? Okay. Yeah, one more question.
Actually, you started your presentation with a description that this problem is required to describe completeness.
Yes.
So what is the measure of completeness? So how do you measure an extent of completeness?
Well, basically, I don't here yet measure embrittlement or even consider embrittlement. It's just the first step to it, because actually, well, in some case, sorry, can I please switch on to the Thank you. So the first step, of course, is to enter this homogeneity tensor to somehow consider brittleness. And again, there are some models of brittleness which introduce some strains induced by brittleness or some potentials. Basically, I don't know a lot about the potentials, only about some strains models, but still they can be entered through this chemical potential. That's why it's a good point to start, because I can add everything based on all the linear equilibrium thermodynamics approach, not phenomenological.
Okay, thank you. Any other questions?
May I ask a question?
Yeah.
In your process, is it required to use some standard definitions for entropy or just classical?
It's a classic one.
Okay, thanks a lot again for your report. And now the next person, Sargsyan well. And it will be an online presentation. And the title is Moment Membrane Dynamic Theory of Elastics in Shells and Variation Principles. Yeah, and the speaker is from Shirak State University of Armenia. So well, we can hear you. Yeah, now we can hear you.
May I speak?
Yes,
Yeah,
of course, please start.
Excuse me for my little English. Moment membrane dynamic theory of elastic thin shells and the variational principles. We will proceed from the general variation principle of Hugh-Washizu for the linear moment theory of elasticity with independent fields of transition and rotation. Please, the next slide. That is equation first, where A is density of potential energy of deformation. Please, the next slide. Nu, lambda, alpha, gamma, epsilon, beta are elastic constants. The general Hugh-Washizu variational principle 1 implies the basic equation of motion, elasticity relation, and geometrical relation of the moment theory of elasticity with independent displacement and the rotation, as well as natural boundary condition of the front surfaces of the shell and the lateral surface of the shell. Basis hypothesis: displacement and the rotations, deformation and the bend torsion, stresses and moment stresses. The hypothesis accepted below can be considered in kinematic and static. Please, the next slide. The essence of the main kinematic hypothesis is the assumption of the constancy of all components of the displacement vector and the vector of independent rotation along the coordinate z that are relation 9. Second, along with the kinematic hypothesis, they are static assumptions. In the corresponding physical relations about the smallness of the normal stresses sigma 3 in comparison with the stress sigma E. of the moment stresses nu 3e in comparison with the nu EE. Stresses sigma 3e in comparison with the sigma E3. Moment stresses nu 3e comparison with the nu E3. We will assume that the shell is thin. Note that the acceptance hypothesis correspond to the initial approximation of the asymptotic method of integration of the boundary value problem of the moment theory of elasticity with independent fields of displacement and rotation in a thin region of the shear. Pass on the accepted hypothesis from the basic equation of the moment theory of elasticity with independent fields of displacement and rotation for deformations, bends, torsions, stresses, and moment stresses we obtain. For deformation and the bending torsions that are relation 10. Where we have relations 11. For stresses and the moment stresses, we have a relation. Please, the next slide. We have relation 12. Relation 13 are average forces and the moments. General variation principle of the Hu-Washizu type passes equations and boundary condition of the moment membrane dynamic theory of elastic thin shear. If we take as a basis the Hu-Washizu variational principle for a three-dimensional moment dynamic theory of elasticity with independent displacement and rotation 1, substituting displacement and rotations 9, deformation and bending torsion 10, stresses and the moment stresses 12, after performing the integration over z from minus h to plus h, we arrive at the similar principle of the moment membrane theory of elastic thin shears. Please, the next slide. That is equation 14, where A0, please, the next slide. Next slide, please. Where A0 is density of potential energy of deformation. The basis equations and boundary condition of the moment membrane dynamic theory of elastic thin shears follow from the general variation equation 14. Equations of motion (16), physical relations of elasticity 17, and the geometric relation 18. Boundary condition 19 and 12. The principle of possible displacement and the basic energy equality of the moment membrane dynamic theory of elastic thin shear. That equation 21. the variation principle of possible displacement 21 of the moment membrane dynamic theory of elastic thin shells is the basis for the application of variational methods for solving boundary value problem in this theory, as well as for the same purpose for the development of a variant of the application of the finite element method. We equate the displacement UEW and the free rotations omega E, omega 3, and some point in time with those displacement and the rotations that at the same point will actually take place over time data. In that case, we have 22. Bearing in mind 22, equation 21 takes the form 23. Where K0 is the kinetic energy of the shell movement and U0 is the potential deformation, potential energy deformation of the shell. 24 and 25. Equation 23 is the main energy equality for the moment membrane's dynamic. This is the next slide. Equation 23 is the main energy equality for the moment membrane dynamic theory of elastic thin shells, on the basis of which we accept that the total increment in time of the kinetic and potential energy of deformation is equal to the increment of the work performed by the external forces moments of the system. The basis energy equation 23 can be used to prove the unequivalence theorem of the solution of the initial boundary value problem of the moment membrane's dynamic theory of elastic thin shells. A case, the causes of deformation and the motion of the shell harmonically change in time. 26. Displacement occur in the shells UE. Please, the next slide. In this case, the system of equation of motion will take the form, and let us introduce two displacement amplitudes and the rotation amplitude, multiply equations motion in turn by delta UE, delta W, delta omega E, delta omega 3, sum up the obtained equations and integrate over the region S of the middle surface of the shells. After some transformation, we obtain equation 28. Where 29, 30. When suppose that the amplitude of forces and moments are subject variation, two variations, we have equation 33. Please, next slide. Next slide, please. And the Hamilton type principle in the moment membrane dynamic theory of elastic thin shears. That equations 35. Please next slide. The Hamilton's type principle of the moment membrane dynamic theory of elastic thin shears. This is equations 35. Thank you for attention.
And thanks a lot for your presentation. Dear colleagues, any questions? I think we have 1 minute for questions for the next presentation. Okay, in this case, thanks a lot for your presentation again. And the next report will be done by Fomicheva Maria. With Vilchevskaya E.A, Bessonov and Professor Muller. Maria is from St. Petersburg Polytechnic University, and she will talk about modeling of granular media grinding process with a variable viscosity coefficient.
So, hello everyone, my name is Maria Fomicheva, and today I'm going to tell you about the modeling of granular media grinding process with variable viscosity coefficient. First of all, I tried to answer the question why we consider the granular media and why it's a grinding process. And I think that you will agree with me that the granular media are very common in our daily life, and also they are very common in different technological processes. And one of the important part of this technological process is the bleeding or cleaning that granular media. For example, the bleeding of granular media is used to create mineral fertilizers, plastics, seeds, and different medicines, etc. And there are many scientific papers which describe the experimental data and behavior of the granular media, but unfortunately, they are not one common and good theory that could describe and explain the behavior of the granular media and bleeding process. And that's why I tried to consider this problem in my model. So let's start with the problem statement. Here you can see so-called funnel-shaped crusher. And this funnel-shaped crusher has some dimensions. And also at the outlet, we have a mirror electron, and it narrows out to L0. And we expect that in this area will be higher pressure than in other parts of the funnel-shaped crusher. And also in this area, the particles will be decreased in size and crushed. And I think it's the first question which you have. Why here in this picture we have so good spherical particles? Because in the real life the particles are not like a sphere. But I want to emphasize that we use a special description for this problem. And for example, and it means that in each point of this funnel-shaped crusher, we consider representative volume. And this representative volume which could contain different particles with different sizes and different shapes. And we use the average characteristics of these particles. And just for visualization, we show like one particles with like a big size and big moment of inertia. And when we apply some pressure to this representative volume, the shape and also size of these particles could change, but also the number of particles could change. And that we one more time take a average, make a averaging process and find the average characteristics of this volume and use them in our equation. So here you can see the system of equation which we use to solve this problem. We consider the balance of momentum, mass balance, and also the kinetic equation for the inertia tensor. And the first two equations help us to find the stresses, pressures, and velocities of the granular media, and the third equation helps us to describe the breathing process. And here you can see the moment of inertia and this geometrical moment of inertia. And when we know the distribution of the moment of inertia, we could also understand the distribution of size of the particles. And the important part of this equation is the right part, because here we have a source term, and this source term corresponds to the different processes in the material. For example, when we have some chemical process or some fast transitions, and also it could be used when the material crushed, and we used to describe the breathing process with this equation. So we consider the viscous material, and also we assume that the viscosity coefficient of this material depends on the moment of inertia, and it depends on the size of particles. And also the important equation here is dense. So this is Sandstone that describes our breathing process, and here you can see inverse of the particle toughness and also pressure of the material, and then moment of inertia and minimum moment of inertia. So we assume that there is some minimum moment of inertia or minimum size of the particles, and after this boundary value, the particles don't attach. And to find and to assume some relationship between the viscosity coefficient and the moment of inertia, we try to use this experimental data. The left plot, you can see the relationship between the viscosity coefficient and the diameter of particles. And we found this information in some scientific paper, and we use this information, and we suggest to use this equation, and we use the expression in our formula. So one more time about the boundary and initial condition. So here at the beginning, at the initial point of time, the pressure is empty, and then the continuous stream of bulk material goes through the pressures. And also we assume that at the beginning the particles have the same diameter, the same moment of inertia in 0, and also we assume that at the inlet surface we have some initial pressure. At the outlet we don't have pressure because the particles go through the free space. And so about the boundary and initial condition, and one more time the system of equations, mass balance, kinetic equation for the inertia tensor, and also balance of momentum. And to solve this system of equation, we use a numerical solution, and then a solution to this problem is found by using the different definitive different methods and schemes, and we create code using the C++ program language. And to check our numerical solution, we consider a simple problem of so-called poison problem, and compare our numerical solution with analytical one. And here you can see in this comparison, the blue solid line is analytical solution, and the points are related to the numerical solution. And you can see that this has a good accuracy, and that's why we use this numerical solution for our main problem. So here you can see a non-stationary solution with distribution of the absolute value of the horizontal velocity in the pressure in different 4 points of time. And the last picture related to the stationary solution, and you can see that the absolute value of the horizontal velocity is decreased in time, and also the area in which the area is non-zero horizontal velocity increased in time. So here you can see the same slide for the vertical velocities, and we also see that the initial point of time there are dot particles and the very small velocity in the middle of the vessel, but at the stationary solution for the last point of time, you can see that the maximum of vertical velocity located near the narrow region, near the free space, and also we have two big red areas with a very small or zero vertical velocity. And here you can see a comparison of four stages of four fields. The first picture is related to the pressure. The second one is moment of inertia, and the horizontal and vertical velocity one more time. So you can see that here at the narrow region we have like a green yellow area with a high pressure, and in this area due to the high pressure we have a small moment of inertia, and also we have here this picture the green area of the green area, and it means that here the particle doesn't achieve the minimum moment of inertia, but we could see to the move to the last picture, and we could understand that in this area the vertical velocities are very high, and it means that the particles located not so very time in this area, and it doesn't so here you can see some plots with more detailed explanation, and here you can see the comparison of the horizontal and vertical velocities for a constant and variable viscosity coefficient. So the solid part is related to the variable coefficient, velocity coefficient, sorry, viscosity coefficient, and the dotted line is related to the constant one. And you can see that there are some difference in 4 or 3 times, and it means that it is very important to understand the relationship between the material properties and the parameters in our problem. And here, the main slide of my presentation, we can see the distribution of the moment of inertia in different medium viscosity. So, as I mentioned earlier, we have this equation to describe the viscosity coefficient and the moment of inertia, and we have some parameter of lambda in this equation. And when lambda is equal to 0, it means that the viscosity coefficient is constant, and we see that at the beginning, so at the wall of the our funnel shape pressure, and in the center of funnel shape pressure, we have a very different high difference between the moment of inertia. And when the viscosity coefficient is decreased, and also we could see that the distribution that the moment of inertia is more distributed. And one more time. So, summary, we consider the funnel shape pressure and the moving forces and leading forces of the granular media in them, and we consider the balance of mass and balance of momentum and kinetic equation for the moment of inertia to solve this problem. We consider the structural changes, and we suggest some new differences between the viscosity coefficient and the moment of inertia, and then source them from the kinetic equation to explain and to describe the excluding forces, and also the distribution of velocity, pressure, moment of inertia, and viscosity coefficient of the medium was obtained and discussed. For your attention. Okay, thanks a lot for presentation. Yeah, any questions? Yeah, please.
Did I understand correctly that actually you consider simple cubic lattice of particles in the equation, right? Simple cubic. So actually, I would maybe right? Simple cubic. Well, yes. Well, the particles, as I understood, are not in lattice. They can move, yes, but initially. Initially.
And not just initially, but during the whole period.
Okay, but my question is probably the result will depend on initial concentration of the particles. If you start from simple cubic, then not maximal, just concentration of particles is 0.52. 0.52. So for if you go to say BCC lattice, body centered cubic, so it means so there is one particle in between. So then concentration will be, I don't remember exactly, but something like 0.7 probably. And a random one is in between them, which is 0.63. So and I think if you build two bounds, so one for simple cubic and one for BCC, then your real result, practical result, will be in between them. So my suggestion is just to consider in the future, to consider another lattice and see how it affects the result.
That's a suggestion, not a question. Okay, thank you. And any questions or suggestions? Well, in that case, thanks again. And the next report will be made online by Dudin D.S with Keller I.E from Institute of Continuous Media Mechanics of Russian Federation. And the title is Interdiffusion Description at Elastic Body with Microstructure Changing by Macro Approach.
With your pleasure, I will show my screen.
Do we have your presentation or not?
Yes, but yeah, I can show my screen, but
yeah, we will show it instead of you.
Do you see my screen?
Yeah.
Oh, it's fine. My name is Dmitry. The theme of my report is related to the interdiffusion with coupled physical and mechanical processes. There are many aspects that I want to tell about, but since I don't have much time, in this report, I will focus mainly on the second point of the outline, namely on the macro approach features. Also, I will report the fact that we want to describe by which approach, and will present the main work results. Where is the following experiment? Aluminum zinc alloy sample undergoes the intensive plastic strains. During the test, a strong grinding of the grain size and an abnormally fast decomposition of aluminum zinc solid solution were. The decay rate can be estimated by the diffusion coefficient by 8 orders of magnitude greater than the usual thermal one. Goal is to determine this fast diffusion coefficient depending on the usual thermal diffusivities. This process can be modeling of this process can be carried out in the framework of the two approaches. The first of them is the mixture theory, presented on the left side. Here, this theory is based on the hypothesis of interacting and interpenetrating continuums. Thus, the balance mass equations, the momentum balance equations, and all other necessary laws are written for each component separately. Then we can go from the component balance equations to the equations for an effective continuum. From a phenomenological point of view, this procedure seems unnecessary. Therefore, here, an alternative approach arises, presented on the right side. It's named the effective continuum theory. It's based on the hypothesis of an effective continuum particle. It allows us also write the balance equations of mass for each component and other necessary laws, but for an effective continuum initially. It should be noted that the complete equation system in effective continuum theory isn't derived from the mixture theory. It's only possible when the velocity in effective continuum theory is the barycentric velocity. In our work, we will use exactly the effective continuum theory approach. Before using this approach, the main question is to determine the effective continuum particle. Here and further on, the large omega is the ratio of an actual macroparticle volume to the reference one. There are 5 main definitions of the macroparticle, depending on the selected systems. The first one is the center of mass system. Here, the total mass in the macroparticle volume doesn't change with time. The second system is the particle system. Here, already the total number of particles in a macroparticle volume doesn't change with time. In the fixed system, a current macroparticle volume always coincides with the reference particle volume. Next is the Keturf system, in which is assumed, for example, the total number of A particles is constant over time. And finally, we have the marker system, in which the current macroparticle volume is represented by a sum of individual atom volumes. The mass balance equations for components written in terms of the total time derivatives have the same structure for all systems, but they differ only in the macroparticle velocities. For example, in the center of mass system, there is the barycentric velocity, and correspondingly in the marker system, there is the marker velocity. In this regard, both the diffusion fluxes and the total time derivatives will differ during the transition from one system to another. At the same time, in a number of systems, the diffusion fluxes are linearly dependent. In the Keturf system, the diffusion flux of a component is 0. And finally, the marker system is determined in such a way that here there isn't any connections between the diffusion fluxes. Therefore, atoms can move independently from each other. It should be noted that the balanced mass equations written namely in terms of the partial derivatives are the same for all systems. And moreover, knowing the diffusion fluxes at one system, we can go to the diffusion fluxes in another system. It means that when we solve a purely diffusion problem, all these systems are equivalent. But this complete equivalence disappears when the particle strain and correspondingly the stress are taken into account. In this case, a problem solution will differ from each system. Using the particle definitions, we can deduce the following consequences. In the upper two cases, as well as for the Keturf system, the corresponding laws of the meta conservation are. If we look at the third case, here the W velocity characterizes convective mass transport. Therefore, namely in fixed system, the divergence of this velocity is 0. And finally, in the marker system, the classical form of dense packing condition varies. All the velocities introduced above have its own practical value. The definition choice of the macroparticle velocities should be strongly correlated with the experimental results. For example, in our case, the marker system in which the diffusion fluxes are independent is the best case for the describing of the interdiffusion. Some model problem was solved for which we managed to determine the diffusion coefficient was located in the red frame. According to its structure, it has the form of sequential connection of the simplest diffusion elements. These elements are included in the structure with the certain coefficients that depends on both the elastic and microstructural properties. These Interdiffusivity D3 has the following features. First, it significantly exceeds the usual thermal diffusivity. And secondly, a prerequisite for obtaining this diffusion coefficient is the assumption of fine-grained structure. These features are completely consistent with the experiments that I mentioned at the beginning of the report. Thank you for your attention.
Thanks a lot for your presentation. And any questions? Well, okay, in this case, thank you. And the next report will be made by Urazlin Vladislav in collaboration with Podolskaya E.A. Vladislav is from Peter St. Petersburg University, and the title is Description of the Mechanical Properties of Graphene based on paired interaction potentials.
One day we want to present you the description of the mechanical properties of graphene based on the pair potential in that direction, pair interaction potentials. In this paper, we will research 5 materials: graphene, gum graphene, 6,6,12 graphene, beta graphene, alpha graphene. This material have the similar structures, but we have the different mechanical properties, and the next slide will show us. In this slide, I can say that in this picture, you can see how this material you can construct. A picture is a different focus, and we can see that the chemical vapor can be useful like a copper foil for using that the graphene can grow up in this paper. Here, problem statement, purpose. We want to investigation of mechanical properties, and we want to construct the general theorem of these materials, like a general theory of allotropic modifications of the carbon, and the problem obtaining general form of rotations, and the obtaining the micro and macro material properties. And the last one, construction of the pair direction potential. Mathematical model, we're going to use the tensors operation mathematical models, and from the geometrical properties of the atoms, we want to construct the 4 Frank tensors, and we will describe our material by the linear recrutation. Now, the first type of graphene, it's an alpha graphene. In figure 1.1, this is how it looks like. But the right figure is a simplified model, and the main idea is that hexagon have a vertex, and in this vertex we have a big atom. In this big atom we have the nearest atoms, and this atom has the biggest mass of these constructions, and we have the beams. One type of beams which will have the two microparameters, CA1 and CD1. The second structure is a gamma graphene, and in this structure we have the second type of beam, which represented that black color. And the idea was the same, that the masses of the ignored atoms placed to the vertices, near vertices. It's a better graphene, this similar, but the length of another beams more than the like a very small red beams, very small black beams. And this is the unit cell. Unit cell using for find out the value of the area. Now we want to represent main formulas. A nu is a tensor of second rank. CA and CD is microparameters, which are according to the different deformations for different directions. This is the definition on the formula two brackets, and why we can to construct the general theory, because I can use in one fourth tensor, I can use the another beams, and I can use the like term. For example, if we use the gamma graphene, we have a two term in formula 3. But if it's a gamma graphene, we have I'm sorry, alpha graphene, we have one term. This is the example of how was chosen the basis. This is the ores, and in this figure you can see that all of our structure has only these types of nodes. It's the imagination of length and more stable structure, and the area between the cell was found. Stiffness tensor of gamma graphene for 4 franc is a plane, and we have 4 independent values, and the C66 have parameters like in the C11 and C12, C12, C22, it's a symmetric tensor. That's why in this case we have a C21, it's equal to C12. And the Young's modulus equation ratio, this is how we will find what is the value of microparameters. So in this slide, I'm going to show that the macroparameters of 4 franc tensor have the microparameters CA1, CD1, CA2, and CD2. CA2 and CD2 is microparameters of the second beam. It was a black beam. And now what we have done? Well, our model, using that we have already know what is the value of coefficient ratio and the Young's modulus. That's why we have built the functional, and this functional we want to use that which is of these parameters, because CYY divided by C12 is a function who depends on 4 parameters, and we have only 2 value, and from these 2 values we wanted to know 4 parameters of our functions. For that, we're using the conditions. This condition is the stable equilibrium, and of course is for 4 rank tensor, and the second rank tensor is a positive definite. And next, we're going to show that all microparameters will be the positive. It's a more general material, 6612 graphene, and now we unit cell another, and the imagination of we have a third type, C length, and we have CA3 and CD3. And of course, it has a different area in cell. This is the example, like a scheme, how from another material to another structure we can go to, like, from the more general case and the alpha graphene, gamma graphene, and beta graphene. In these cases, we shoot to C equals 0. It's a third length of beam. Because in this construct, we have three types of beam: black, red, and green. So, according to that model, we have found the microparameters, the value of microparameters, and I can say that the smallest microparameters can show that in this connection, our material will be destroyed. And the second table, we can see that we have our materials and our macroparameters and compare with the experimental results. Now I should say that the material has an isotropic symmetry, but in this theory, material is isotropic. But next slides, I'm going to show that it doesn't matter so bad, because the difference between two directions is not so big. Now this is the example of the behavior of material. It shows us that we can use the linear model. It's zigzag direction and armchair direction. Oh, okay. And if we want to constrain the field to destroy our material, we should to construct our potential. Potential is that we think that we have two atoms, and this potential connects our two atoms. And according to our microparameters was founded to previous slides, we're going to choose the value of this compass 149 meters, and the critical stress is 107.5 gigapascals. And in results, we are comparing two lines, and we can see that the more bright line, it's our result, and the not so bright, it's a result from the article in picture right, we can see the places the connection is failed, and we can say that we have a sheet with size 10 nanometers on 10 nanometers, and we have a periodic boundary conditions, and that's why we have two walls. And the next step, we have found the values, and was compared with another article, but the highest of stress was in the zigzag direction. But if we compare with another article, we have not so big values of it, and that's why the most results haven't converged with theory was the stress of the zigzag direction. Conclusions. And I'm going to show that we have like general theory that we can use to construct and predict how a material, also for graphene and graphene, maybe and another atomic modifiers of carbon, can destroy it, in which parameters it can be destroyed, which parameters of microstructure we should use to model our material, and we have the potential for deformation. Potential, we have the two because we have a two direction, and the first and the second potential can show us that, or of course, I forgot to say that potential is a polynomial functions. That's in the three segment. One segment is the microparameters positive, the second segment of the microparameters is negative, and the first segment where is our connection is zero. Zero. Thank you for your attention. Any questions?
Thanks for your presentation and any questions.
Thank you for your presentation. Question. Did I understand correctly that you compared your results with
It's a computer, not like a material that you can.
Numerical, yeah? Any other questions?
Yeah. Can you show typical value of young models for graphene and the young models in countries?
No, it's like go interact forward to.
I see value of definite is more volume. No?
Maybe, but I
mean, graphene is have big strength and more than K. So they will have young models showing to Miller perspective. So
okay, maybe I have a mistake because it's not a power of two, it's only in one power, even for mixture.
Right. That doesn't make sense. I mean, the question is that you have a 300 Pascals here, and typically it is 1,000 times bigger. Even more.
And it's not meters, it's yeah, maybe millimeters. In that case, it will make sense. Just check it, okay? Okay, another question. Well, in this case, thanks a lot for your presentation. And the next person, Shorkin Vladimir, in collaboration with Vilchevskaya E.N. From Morozov State University of Russian Federation. The title is Micropolar Theory with Non-Local Potential Interactions.
Thank you. This work is micropolar theory with non-local potential interaction. Authors Shorkin and Vilchevskaya. Outline. A homogeneous isotropic elastic body is subject to an external electric field is considered. The aim of the work is to identify the effect of polarization on the mechanical properties of the solid dielectric within the framework of a non-local model of the micropolar continuum. The work has three parts. The first part is non-local model of an elastic body. Second part is calculation of the mechanical properties changed due to polarization. And third part is examples. The continuum and the microscopic viewpoint. We consider an equilibrium state of the body B subjected to an external electric field. The body consists of rigid dipole Q small with the dipole moment D small. The relative permittivity epsilon and the polarization coefficients he now for weak electric field polarization P is proportional to electric intensity E. The material is homogeneous and linearly elastic. The continuum and the microscopic viewpoint. Here we present the idea of describing the properties of a continuum be describing the properties of a discrete ensemble of oriented body points. Here is transition from the solid body to particle ensemble B small. A continuous body has mass, potential energy, and dipole moment. They are equal to the sum of the masses, potential energy, and dipole moments of the delta B part here. The mass, potential energy, and dipole moment of the delta B parts are equal to the product of the density be the volume, density and volume. The density is defined and at one of the volume point. Here is R big. Therefore, the product is defined at the same point. So when calculating the mass, potential energy, and dipole moment of a body using integral sums, the values are equal to the mass, potential energy, and dipole moment of a discrete ensemble of oriented body points, this ensemble. Therefore, the potential energy of the entire body is the result of the interaction of oriented body points. These body points are ideal particles. This interaction is similar to the interaction of microparticles of microdipoles. Properties of microparticles. The delta B part are formed by rigid microparticles. Microparticles have no internal potential energy. A microparticle has a potential energy of interactions. This energy is calculated using the Stockmayer pair potential. This averaging properties of body points. Energy of body points, average properties of body points. A body point B small has mass m equal to the masses of the microparticles Q in delta B, this sum. Reference position vector R small, current position vector R big, displacement vector U, dipole moment D big, and polarization vector P. Energy of body points. It is equal to the sum of the internal energy of the delta B particle and the energy of its interaction with the environment. If the number of delta B particles into which the body B is divided tend to infinity and their diameter tend to 0, then the limit of internal energy is 0. This interaction. The energy of interaction with the environment is equal to the sum of paired and triple interaction with the same delta B particles. This interaction, this sum of pair energy interaction and this triple pair energy interaction. Now, locality properties of a continuous medium. If the number of delta B particle tend to infinity and their diameter tend to 0, oriented body point of a discrete ensemble are equivalent to infinitesimal particles of a continuous medium, dB. We have the potential of paired and triple interactions these particles. This paired potential, this triple contention. This is an example. The first diagram illustrates the dipole-dipole interaction. The second diagram illustrated the potential of pair interaction of point bodies when they approach each other. Now, locality properties describe the pair and triple potentials. The potential energy distribution density for non-local interactions is given by this expression. Local properties change due to an electric field. We compare the tensor of the material constant of a linearly elastic material in the presence and absence of an electric field. The classical linearly model is quadratic approximation of the dependence of the volume density of potential energy on small changes in kinematic characteristic. The coefficient of this approximation determines the properties of the material. The dependence of energy on kinematic is unknown. Therefore, they are determined experimentally. In our case, we know this dependence. For the linearly elastic material, the paired and triple potential are second-degree polynomials of the deformation characteristics. We have two cases. Case 1, without the electric field, the polarization vector is 0. Vectors that are used to describe deformation is delta 1, 2 and delta 1, 3. Volumetric strain energy density is this equilibrium. This tensor Pu is initial stress. Tensor of the material constant is Puu. The matrix tensor Puu in Voigt notation. Without polarization, the materials is homogeneous and isotropic. We have equality to matrix. This is classic matrix, lambda mu as Lamé parameters. This is matrix we have eta, chi, and epsilon a function of parameters of potential. So we can express parameter of interaction in terms of Lamé parameters. Potential of polarized material. Case 2, there is an electric field. The material is already polarized in the reference state, P no equal 0. Pair potential. This is pair potential. This potential have two elements, this and this. The transition from the reference of configuration to the actual one is carried out using the relative displacements and relative rotation, delta U here and here, changing the orientation angle P1 relative P2 relative P1, changing the orientation angle P1 relative vector L, big, changing the orientation angle P2 relative this vector, and changing the orientation angle L big relative L small. This is rotor U. We have increment of the volume density of the potential energy. This is big expression. Here, delta V star is classical expression. The vector I3 of the orthonormal basis is discrete along the vector E of the electric field strength. In this basis, the matrix of the tensor components, tensor P U minus B, beta U minus beta, has this form. Here we consider only one tensor of material properties. It can be seen that L components with index 3 are equal to 0. That is, there are no infinitesimal rotation around the direction of polarization. The examples. The calculation is carried out for diatomic silicon. Here is parameters for this calculation. Here is linear is depends of the polarization of the electric field strength. we have two cases. Case one is for small electric field strength here. P is proportional electric field strength. At case two is saturation polarization. Here P equal product N and D. This second case, this. Two examples of polarization are considered. In the first case, P is proportional E. E equals this number. Maximum energy of the orientation interaction of volume unit WP is this number. This energy is this element. This number very little compared to the maximum interaction energy of the unit of the volume of the material without taking into account the polarization phi 0,2, this number. In the second case, P equal ND, maximum energy of the orientation interaction of volume WP commensurate with to the number phi 0,2. Conclusion is strong electric field. Polarization can significantly affect of the properties of the material. Thank you very much.
Thanks a lot for the presentation. Any questions? Well, if no questions, then thanks again. And the last presentation will be made by Dudin D.S in collaboration with Grigoreva P.M, also from it is a great St. University, and the title is Dynamic on the simplest Keller medium in the vicinity of a non-linear equilibrium.
Ты, Господи.
Good evening, everyone. My name is Dudin, and I will present you how we see the Grigoreva work research in dynamics of the simplest elements medium in the vicinity of a non-linear equilibrium. First of all, I'll I'll tell you about motivation and model. After that, we'll see elastic simplest nonlinear reduced scaling medium, and then we make some linearization near nonlinear prestressed state. And finally, we find out what form will have weight and stability of the medium in the nonlinear prestressed state. Motivation. Kelvin's medium is a Ksenia medium with dynamic spin. It consists of axisymmetric particles that can move and rotate in all directions. Their rotation about the axis, on axis, doesn't produce any stresses. This term was introduced by Zhilin and now forms a part of dictionary of modern mechanics. There you can see some analogy between Kelvin's medium and ferromagnets. And so on. Okay, motivation. We want to introduce reduced media because it is single negative acoustic metamaterial with respect to those shear rotation waves, which are polarized against the spin rotation. This even get. Acoustic metamaterials have anomalous wave properties. They are used for walking. Nonlinear stress state in the reduced and full Ksenia medium changes the effective elastic constants and influence wave propagation and stability, providing a new way to lose the stability of the material. And finally, constitutive fluctuations of Kelvin's medium are a specific case of the Ksenia medium, and the dynamic term is different due to gyroscopic effects. And the main question: what will be for the simplest reduced Kelvin's medium in the nonlinear prestressed state? Okay, reduced medium. Our energy doesn't depend on gradient P, and there are no coupled stress tensor, but stress tensor we will discuss. We will use in two different forms: S tau stress tensor and T first Piotrków stress tensor. So balance of force and balance of torque. There are no new. Constitutive equations for the reduced Ksenia media we will use in Zhilin's form. For reduced Kelvin's media, the strain energy depends only on those strains that don't include gradient P and P. We choose U as a form of G and gamma, tilde gamma. You can see them. They include all independent strain measures according to Grigoreva P.M. Note that in the vicinity of the natural state, G and gamma is equal to linear the linear strain tensors. So after some tensor algebra, we obtain our tau and T. So we consider physically linear, but geometrically nonlinear medium. Strain energy is a quadratic form on nonlinear strain tensors G and gamma. G is symmetric tensor, and there is no term with G and gamma because of isotropy of our medium. Okay, so we have this form for tau and this form for T, and now we make some linearization near our stress state, prestressed state, and our type of deformation is spherical deformation. You can see that compression or tension, and there is no any rotations stresses. So we have TS, T1, subindex S denotes quantities in the nonlinear spherical state, strain state. And we will use the gradient operator in the pre-stress configuration nabla S. Simplest reduced Kelvin's medial in the vicinity of a nonlinear spherical states. Some approximations, and after calculations, we have linear part of T in this form, and finally balance of force in the first approximation and balance of moment in the first approximation. Okay, looking for a harmonic solution in time, we can express theta via U. So from the balance of moments, we can substitute this to the balance of force, looking for the plane wave, but it's very tedious and not easy. But we can say that longitudinal and shear waves are not separated, unlike near the natural state, and the equations are much more sophisticated than the vicinity of the natural state. But we can have a look on plane wave propagation along dynamic spins. Port for K equals to plus or minus M0. So reduce spectral problem, and here we write some effective constants. It's not Lamé coefficients. And finally, let's talk some about stability. We don't know if the medium is stable with respect to perturbation or other kind, but if you find instability for this motion, the medium is unstable. Classical physically linear elastic isotropic medium is unstable under strong hydrostatic compression. Doesn't resist shear perturbation. But elastic isotropic SRR and reduced SRR physically linear media either don't resist shear perturbation under high hydrostatic pressure, and in addition can be unstable under strong spherical tension, don't resist rotation perturbation. And the simplest Kelvin's medial isn't isotropic, but it is close to this. So the dynamic term is different, and how will it influence the stability under spherical strain is a question. Plane wave propagation along dynamic spins, we have non-dispersive P waves and a dispersive shear rotation wave in the medium is stable. Now, our preliminary results, it's a new mechanism of instability. The mechanism may exhibit instability under high spherical deformation, and traction or tension depending on elastic constants with respect to volumetric perturbation. No such mechanisms for classic or unusual media or classic media. And also all the mechanism of instability. It also may fail under high contraction, becoming unstable with respect to shear, always if R less than 0.15. Okay, plane wave propagation along dynamic spins. We can see some branch of on the graphics. U rotates against spins, and U rotates in the spins directions. So this equation about polarized again along spins and polarized against spins. Conclusions: we obtained basic equations of the simplest nonlinear Kelvin's medium. We have coupled waves in the vicinity of the nonlinear spherical strain state in contrast to the linear case, and wave propagation along against spins P waves is non-dispersive, may lead to the instability of the material under tension or convection. Shear rotation wave has two dispersive waves, both with certain polarization, one with a band gap and band gap. You can see it. And as in the linear case, but the effective modeling depends on the pre-stressed state. And shear rotational wave may lead to the instability of the material under construction for a certain domain of elastic parameters. We plan to investigate arbitrary direction of wave propagation, other strain states, and other non-linear models. Okay, thank you for your attention.
Thanks a lot for your presentation. Any questions? So my question is, how did you estimate the effective modeling?
Effective modeling.
Yeah, so I see this formula and from why do this formula?
Okay. We first of all we have balance of force and balance of moment. From the balance of moment, we find theta via U and
Micro-rotation.
yes, and put it in the balance of force. And now we just want to look at U with in this form with K equal plus minus M0. And after calculations and after
Okay, so you have calculated it.
Calculated,
And do
yes.
you have any numerical or experiment with other to compare modeling something? Just to understand if it is correct?
No. Now it's in work and it's our future.
Okay, so and where do you want to apply this model? So in future you want to compare it with some
Yes, of
concrete
course.
models?
Yes.
Okay.
And also, why do you use spherical strains or spherical tension? Just because of the symmetry, or
Because of the symmetry, it's easier and it's new way to obtain media near some. Because it's symmetry.
Okay.
So,
Okay, thank you. And any questions from Mark? Okay, in this case, I think that it's all. Thank you very much for your attending this session.